Now for the notes on day 1 of Unit 6. We're going to talk about the properties of definite integrals. Just so you know, definite integrals just means it has boundaries on the integral sign. When you were doing antiderivatives last unit, that was indefinite integrals because there were no boundaries. So let's look at the first property. Again, just to be clear, it's these boundaries right here, in this case the a and the a, that make it a definite integral. So, the first property is that if your boundaries are the same, then it's always going to be 0. Um, the integral finds area, and your boundaries tell you where to start and where to stop. So if you're starting and stopping the exact same place, your area is 0. You can think about it just like this. If you don't walk anywhere, then you've covered no ground and you've covered no area. So if the boundaries on the top and the bottom are the same, then the area is just 0. Okay, the second property. In general, when you're setting up an integral, you should always put the lower number on the bottom and the bigger number on top. If you ever see it set up opposite, then to flip the boundaries, you must also change the sign to be a negative. Basically, the idea is if you're moving forward, then it's positive area. If you're moving backwards, then it becomes negative because you're losing ground. So, for example, if we were drawing this graph right here, as I move forward, we'll just have the red line represent where we're moving. As I move forward, I'm adding up all that area that I'm getting. So I'm accumulating area, accumulating area, accumulating area. So I'm getting it more area each time. But if I move backwards, then I'm losing area each time. My total area is decreasing. So if you want to switch the boundaries, you also have to change the sign to be negative. The third property says let A be less than B be less than C. In other words, A is the smallest number, C is the bigger number, and then B would be in between. So this just says that you can split up an integral into two pieces. So for example, if you're going from 1, 2, 3, the integral from 1 to 3, whoops, sorry about that. Trying to highlight, there we go. The integral from 1 to 3 is the same thing as doing the integral from 1 to 2 plus 2 to 3. That's the idea. You can split it up in two pieces, add them together, and it's the same as the whole piece. Pretty intuitive. So over here, for example, if we were to do the integral from 0 to 2, and then do the integral from 2 to 4, that's the same thing as the integral from 0 to 4, the whole thing. That's all that means. You're allowed to break it up and get the same result. So let's move on to the fourth property, which simply says that if you have a constant, you're allowed to pull it out front. The important thing there is, let's say you actually have an equation. Let's say you have the integral of 2x from 0 to 3. Actually, let's just make it x, integral of x. Then if you find that answer to be, let's see, 9/2, then if they next gave you the integral 2x dx, then you know that all you have to do to get your answer is multiply by 2, and it's just going to be 9, because you're allowed to pull this 2 out front if you want to. Okay, the fifth and final property is that if you're adding or subtracting pieces, you can split them up into two different integrals. This adding and subtracting property is something that holds true for everything we do in calculus. It works for limits, it works for derivatives, it works for integrals, it's going to work for series that we do later on in the year. So if you're adding or subtracting, you're allowed to split it up into two pieces. That's the idea. So these make up the properties of integrals, and it's very important that you understand how to use them. So we're going to do a few examples to show you how to apply them. So first example. Let's say that we're given that for some function f of x, the integral from 0 to 4 is 7. And you're told for some other function, g of x, the integral from 0 to 4 is 4. Remember, integral just means area under the curve, so what this is really implying is that the area under f of x from 0 to 4 adds up to 7, and that the area under g of x from 0 to 4 adds up to 4. So now we could ask a few questions about the area of these two functions. So for example, they could ask, okay, what's the integral of f of x from 3 to 3? Well, if you look back at our very first property, we know that if the boundaries are the same on the top and the bottom, that means we have no area because we didn't go anywhere. So the answer would just be 0. That one I really didn't even need the info up top. Okay, let's say we do the integral from 4 to 0 of g of x dx is equal to negative 4. I got a little ahead of myself there, sorry. It is negative 4, let's back up. It is negative 4 because if you look, the boundaries are the same here as they are here, except that they've been flipped over. So, if you flip the boundaries, then you have to flip the sign of the answer. So from 0 to 4 going forward, your answer is 4. From 4 to 0, traveling backwards, your answer is negative 4. Okay, one more with these givens, then we'll try a new one. We'll do the integral from 0 to 4 of f of x minus 3g of x dx. Okay, now once you get used to these problems, you don't necessarily have to do all the work I'm about to show. This is basically just going to boil down to substitution. But just to apply all the properties we just learned, the very final property, the fifth property, said if we're adding or subtracting, we can split it up into two pieces. So that's the first thing I'll do. I'll write it as the integral from 0 to 4 of f of x minus the integral from 0 to 4 of 3 times g of x. Also, one of the properties in there said that we're allowed to pull constants out front. So let's rewrite it again and put the 3 out front. Now it's simply a matter of plugging in what we know. We know that the integral from 0 to 4 is 7. I'm just using the givens up top. So I'm just applying the givens right here. Up. There we go. Just applying that given. I know that's 7. Then I do minus 3 times. I know that the integral of g of x is 4. So 3 times 4. So we get 7 minus 12, which is negative 5. And it's fine to get negatives on these. That just implies that your total area tends to be under the x-axis instead of above it. So that's the first example. Let's try another. Let's say that we're given that the integral from 1 to 5 of h of x is equal to 10, and the integral from 1 to 2 of h of x is equal to 7. So this time we're dealing with the same function, h of x, for both of them, but we're given the area under two different boundaries. First, from 1 to 5, our total area is 10, and from 1 to 2, our total area is 7. So first, let's try this. What would be the integral from 2 to 1 of 5 times h of x dx? Okay, well if you look, there's two things that have happened. The boundaries have been flipped upside down. We're now going from 2 to 1 instead of from 1 to 2. And we've multiplied by 5. So flipping it from 1 to 2 to 2 to 1 makes it negative. And we also need to multiply by 5. So we get 35. Because we know that the integral from 1 to 2 is 7. So if we multiply by 5, we get 35. And because we flipped the boundaries, we have to make it negative. Okay, now let's say we do the integral from 2 to 5 of h of x. Well, if you look, neither of our functions, or neither of our givens, excuse me, have the boundaries 2 to 5. But if you look carefully and think about the number line, here's what we have. If we were to go from 1 to 5, we're given that from 1 to 5, the total area is 10. We're also given that the area from 1 to 2 is 7. So I got both of those from my given. Now what they're asking us is what would the area be from 2 to 5? So hopefully you can tell just by looking that that would have to be 3. Okay, the reason is that property. Let's go back and look at it. It's this property number 3 that allows you to split up into two pieces. Okay, it's this property right here. That's the idea we're working from. So if you wanted, you could set it up this way. The integral from 1 to 5 of h of x dx is the same as the integral from 1 to 2 h of x dx plus the integral from 2 to 5 h of x dx. Okay, the integral from 1 to 5 is 10. That's the given. 1 to 2 is 7. And then we're trying to solve for this last one, h of x dx from 2 to 5. So all you do is subtract the 7 over, and that's how we get 3. So that is our final answer for that question. Okay, just one more example, and then we'll be finished. Let's say that we are given that the integral from negative 3 to 1 of f of x is equal to negative 4, and the integral from negative 3 to 1 of g of x equals 11. Sorry, forgot my dx. There we go. And this is our last one. Let's say they ask us to find the integral from 1 to negative 3 of 4gx plus 2f of x dx. Like I said, this really just boils down to substitution. We know that the area for g of x is going to be 11, so we get 4 times 11, just putting 11 in for the g, plus 2 times negative 4 for the f. And I'm going to have to make that whole thing negative because I've flipped the boundaries over. If you notice, this is going from 1 to negative 3. So I have to make my whole answer negative. So I get negative 44 minus 8. So that's negative 36. All right. The practice problems for this section is page 273, number 33 through 45.